Okay, let's consider this arithmetic sum. Okay, now you have each term is greater than the next here. I going from 1 to n of this a sub I plus 1 minus a sub I. And I want to try to get a generalized formula for that. Okay, so now if we start doing the sequence, that sum is going to equal to, okay, if at 1 it's going to be 1 plus 1 is 2, and a sub 2 minus a sub 1, and then it's going to keep going. So you can have a sub 2 minus a sub 1 plus a sub 3 minus a sub 2 plus a sub 4 minus a sub 3. And what you're seeing here is a sub 2, positive a sub 2 is going to cancel with negative a sub 2, sorry. Positive a sub 2 will cancel with negative a sub 2. Positive a sub 3 will cancel with negative a sub 3. And we just generalize that. So it keeps going one term ahead. That's n plus 1 minus that first term, a sub 1. See what I'm talking about? Okay. So this is your generalized formula for that. So in other words, it's saying that in general, I going from 1 to n of a sub I plus 1 minus a sub I will generalize into a sub n plus 1 minus a sub 1. That's your generalized formula. Okay, now let's do something unique here, which was done to discover how to invent calculus. And this guy, this Riemann guy, he came along and he said, the Riemann sum, he said, what happens if I try I plus 1 squared, for this a sub I plus 1, minus I squared. And I take the summation of that with I going from 1 to n. Because he noted that when you square all this, the I squareds will cancel, and you'll be able to find the summation of I. The summation is I goes from 1 to n of I. So in other words, this will turn out to be the summation as I goes from 1 to n of I squared plus 2I plus 1 minus I squared. The I squareds will cancel. Okay? And when that happens, you're going to end up with summation as I goes from 1 to n of the quantity 2I plus 1. Well, now, on the other side of the equation, you also know that that was equal to n plus 1 squared minus 1, the first term of the sum. Okay? Now, we write summation I goes from 1 to n of this 2I plus 1 equals n squared plus 2n plus 1 minus 1. Of course, the ones are going to drop out. Now we have summation as I goes from 1 to n of 2I plus, use the distributive law for summations. The summation as I goes from 1 to n of 1 equals n squared plus 2n can be factored as n times, well, I'm going to factor it yet. Sorry. N squared, just n squared plus 2n. Yeah. So now I'm going to have summation, take the constant out, as I goes from 1 to n of I, plus the summation going up to n of 1 is just going to be n, okay? So it's just going to sum all the way up to n times, right? So you have n there, and that equals n squared plus 2n. And then you have 2 summation I going from 1 to n of I equals n squared plus 2n minus n, like that. So you end up with 2 summation I goes from 1 to n of I equals, well, I'm going to subtract here, n squared plus n, like that, and then I get 2 summation I going from 1 to n of I. Factor out, gets n plus 1 here. I factored out the n, because n times n is n squared, n times 1 is n, okay? Dividing by 2, I'm going to have my formula. Summation as I goes from 1 to n of I is just going to equal to n times n plus 1 over 2. Okay, so that's going to be the sum formula if you're going to just add up I going from 1 to n. Okay, I'll show you what that means. Okay, you know the summation of I going from 1 to n just equals 1 plus 2 plus 3 plus, and so on up to n plus n. Okay, so if I summed it from going from I equal to 1, going from 1 to 3 of this I would get 1 plus 2 plus 3. We stop at 3. 3 is n, okay? That will equal to 1 plus 2 equals 3. 3 plus 3 equals 6, right? From the formula, summation I going from 1 to n of I equal to n times n plus 1 over 2. We set n equal to 3. What happens if we set n equal to 3? Then we get summation as I goes from 1 to 3 of I should equal 3, see I'm substituting in for n, times 3 plus 1 divided by 2. And that's going to equal to 3 times, well, 3 plus 1 is 4, right? 3 times 4 divided by 2. And that's 12 divided by 2, which also equals 6. So we get the same answer, so that means the formula works. Okay? So, I mean, if you wanted to try another one just for fun, summation as I goes from 1 to 4 of I would be 1 plus 2 plus 3 plus 4, which would equal to 1 plus 2 equals 3, 3 plus 3 equals 6, 6 plus 4 equals 10. Okay, now let's try our formula. Summation is I goes from 1 to 4 of I should equal to 4, so we're going to 4, times 4 plus 1 divided by 2. And that equals, well, 4 plus 1 is 5. 4 times 5 is 20. And 20 divided by 2 equals 10. So our formula works, okay? We just tested it. I found a generalized formula to sum numbers from I going from 1 to n of I equal to n times the quantity n plus 1 divided by 2. What's nice about that? Well, let me tell you what's nice about that. What if you're summing up to 1,000? You know, what if your sum is going up to 2230, 2,230? You know, you could just plug it into this formula and find it that way instead of going through all this sum and adding all these terms up. You just put it right into your formula and you get your answer right away. That's the nice thing about these formulas. That's why mathematicians always want to try to find a more concise way to do things, an easier way to do things. It makes life easier. And trust me, physics without math, without a mathematician, is very limited. Physics, anything. A mathematician can help a physicist take physics into the next level, okay? So, and that's with engineering and everything that you have, okay? Now, in the next video that I do on summations, I'm going to prove that the summation as I goes from 1 to n of I squared is going to equal to n times n plus 1 times 2n plus 1, all that divided by 6. I will prove that. So let's try one of those, okay, just for fun. Summation as I goes from 1 to 3. I don't like that summation. Let me make that neater. There we go. That looks a lot better. Okay, the summation as I goes from 1 excuse me, to 3 of I squared. What's that going to equal to? Well, let's do it. Okay, it's going to be 1 squared plus 2 squared plus 3 squared, which would equal to 1 squared is 1, plus 2 squared is 4, so that's 5, plus 3 squared is 6. No, 3 squared is 9, I'm sorry. 9, only doing 1 plus 4 is 5, plus 9, 5 plus 9 is 14. Okay, now let's try it under formula. 3 times 3 plus 1 is 4, times 2 times 3 is 6, plus 1 is 7, divided by 6. Is this going to work? 3 times 4 is 12, and 12 times 7 equals 84. 84 divided by 6. So that's 84 divided by 6. 6 goes into 8 once. And 6 goes into 24 4 times. Guess what? It does work. So that also equals 14. 84 divided by 6 is 14. So this formula works as well. I'm not going to derive it in this video because it takes a little bit more work, but that's basically where the idea for the summation method of calculus, which becomes the integral. This is what Riemann sum was all about. And he used this to, what he did is he would inscribe a set of polygons under a curve and partition them in equal partitions and find the width times the height. Well, the summation would be the width, and times the height of each one of these rectangular regions, and sum them up, and then take the limit as n tends to infinity to get the actual area. He did the inscribed, the circumscribed, and then the partition where it is the mean value height. Okay, and that's where the partition goes to 0. That's the same thing as taking n into infinity. So he used 3 different ways to prove the method of integration for the definite integral. And then he used the binomial theorem to generalize a formula for finding the generalized formula for finding the definite integral to find the area under a curve. Okay, so this is was the foundation of everything right here. He started out with this. He said, if you've got a set of terms, a sub I plus 1 minus a sub I, how can you generalize that into something simple that you can use to find the sum? Okay, and that's what I did here. Okay, that's what I did here. I found the generalized formula. The summation as I goes from 1 to n of a sub I plus 1 minus a sub I generalizes into a sub n plus 1 minus the first term, a sub 1. And then I plugged in the quantity I plus 1 and squared it, and minus I squared. And I compared it to this, and I said, okay, if your I plus 1 term is I plus 1 squared, and your a sub I term is I squared, then that means that you're going to have the generalized n plus 1 term squared minus the first term, which is 1. And then simplified everything, and I discovered that the summation as I goes from 1 to n of I equals, or generalizes to n times the quantity n plus 1 divided by 2. Okay, and then I proved that it worked. I said summation as I goes from 1 to 3 of I equals 1 plus 2 plus 3, which equals 6. And then I set n equal to 3 to see if it would work. And when I set n equal to 3, I got the same answer. So that proved that it's true. And like I said, later on, I will derive the formula. The summation as I goes from 1 to n of I squared equals n times the quantity n plus 1 times the quantity 2n plus 1, all divided by 6. I proved it here for 3. I going from 1 to 3 of I squared equals 1 squared plus 2 squared plus 3 squared, which equaled 14. And then I plugged in equal to 3 into this equation right here to see if it would match this. And when I plugged it in, I got 3 times 4 times 7, all that divided by 6, and that equals 84 divided by 6, which equals 14. So 14 equals 14, so that proves that generalized formula also works. Okay, thank you.